Hello calculus students. In this video we're going to talk about how to use the limit definition of the derivative to find the derivatives of functions. Here are two different versions of the limit definition of the derivative. We can say that f prime of x is equal to the limit as h approaches 0 of f of x plus h subtract f of x divided by h. Notice that this is the limit of the difference quotient as the value of h approaches 0. And we talked about that in the past. We said, well, the difference quotient is the slope of the secant line, and when we take the limit as h goes to 0, that gives us the slope of the tangent line. So notice that this gives us a formula for f prime of x. Now the second equation, f prime of a equals the limit as x approaches a of f of x minus f of a divided by x minus a, is also a definition for the derivative using a limit. But notice that this one gives us the value of the derivative at one particular spot, namely at a. So these two things give us slightly different versions of our derivative. The top definition gives us a formula in terms of x, and the second definition we use when we want to know a specific value of the derivative. So let's put these two formulas to work and see how we can use them. So we're going to ask two different questions. First, we might say, given the function f of x is equal to x squared, find f prime of x. In this case, what I really want to do is use that top formula, because notice I want a general formula for the derivative of x squared. So now I can say that f prime of x equals the limit as h approaches 0. In this case, f of x plus h is x plus h the quantity squared, and f of x is x squared. So now I've filled in everything, and at this point I need to simplify so that I can take my limit. So I'll just recopy my limit symbol, and now I'm going to expand out my numerator. So I have x squared plus 2xh plus h squared minus x squared all over h. And now I can notice that every term in the numerator that does not possess a factor of h has an opposite to cancel with. And this is important because the only way I'm going to be able to take this limit is if I can divide the h out of the denominator. So be on the lookout for this to happen. So now that I've done that, I can cancel h from all the remaining terms. So what I am left with is the limit as h approaches 0 of 2x plus h. At this point, I no longer have to worry about allowing h to be 0. I have no trouble doing that at all. I get 2x plus 0, and I am left with 2x. And this matches up with what we learned in our previous unit using the power rule. X squared, we'd pull the 2 down to the front, subtract 1 off the exponent, and we would come out with 2x, just like we did right here. So there's how we use our first version of the limit definition of the derivative to find a derivative. Now let's suppose that somebody asks us this question. F of x equals x squared, find f prime of 3. This is a scenario where we can actually use the alternative definition. So we can say that f prime of 3 would be equal to the limit as x approaches 3 of f of x, which is x squared, minus f of 3, which is 9, 3 squared, divided by x subtract 3. So notice I've used the second definition, just replacing all the a's with 3's. So now I still have that same problem. The limit in the denominator is 0, so I've got to divide before I can take the limit. So now I say the limit as x approaches 3. I factor x squared minus 9 as x minus 3 times x plus 3. And now I see that the x minus 3's can cancel, and I'm left with the limit as x approaches 3 of x plus 3, and at this point we can allow x to be 3. So we substitute, sum up, and we come out with 6. Now in the previous page we found out that f prime of x was equal to 2x, and if we evaluate this, f prime of 3, we get 2 times 3, which is equal to 6. So if we only want to know one value of the derivative, like all I want to know is f prime of 3, using that second definition is perfectly good. But if I want to do a whole bunch of evaluations, if I wanted to know f prime of 3 and f prime of 5 and f prime of 7 and f prime of 18, then I would much rather use the first definition to get a formula and then use the formula to do my evaluation, because that formula is already simplified for me. So here's a problem for you to try. Given f of x equals x cubed subtract 8, find a formula for f prime of x, so there you're going to use the first definition, and then use the second definition to find f prime of 2. Then go back to your first definition's version and use it to check the second. Make sure you get the same answer going both ways. So pause the video, work out the problem, and then restart to check your work. So let's see how you did. Let's start out by finding the formula for f prime of x using the first version of the definition. So f prime of x is the limit as h approaches 0 of x plus h, the quantity cubed, minus 8, subtract x cubed plus 8 divided by h. I can see right away that the 8's are going to cancel, and now I need to expand out x plus h, the quantity cubed. So the limit as h approaches 0. So at this point, I'm going to have x cubed. And if you've forgotten how to expand this out, don't forget you can use Pascal's triangle to get your coefficients. So we have x cubed with a coefficient of 1. Then we have 3x squared h, using up the coefficient of 3. Then we have 3xh squared, using up our other coefficient of 3, and then we have h cubed. And then at the end, we still have our minus x cubed to put in here. And we're dividing by h. Now again, notice the same thing is going to happen. Any term in the numerator that doesn't have a factor of h should have a term to cancel with. And sure enough, x cubed and minus x cubed cancel, and that will allow us to reduce out the h. So we did a little reducing here, and now we have the limit as h approaches 0 of 3x squared plus 3xh plus h squared. Allowing the h's to become 0 leaves us with 3x squared. We can check that using our old power rule. We bring the 3 to the front, subtract 1 off the exponent, 3x squared, and the 8 zeroes out. So, now let's find f prime of 2 using our second definition. So f prime of 2 will be the limit as x approaches 2. And now we're going to have in here our x cubed minus 2 cubed over x subtract 2. Now we'll go in here and we'll factor. So we've got the limit as x approaches 2. We're factoring the difference of 2 cubes, so we'll have x minus 2 as our first factor, and x squared plus 2x plus 4 as our second factor. And now we can see that the x subtract 2's will cancel. And we now have the limit as x approaches 2 of x squared plus 2x plus 4, which is 4 plus 4 plus 4, and 4 plus 4 plus 4 is 12. Now let's check by taking f prime of 2 using our previous result. That will be 3 times 2 squared, and 3 times 2 squared is 12. So we see that, yes, we did indeed end up with the correct result. So that's basically how you use the limit definition to take a derivative. So let's see how else we can use this limit definition. In Chapter 3, we learned a whole lot of rules for going in and determining what the derivatives were of certain kinds of functions without actually having to take a limit. We used the limit definition to prove that those rules are actually true. So let's start out with the power rule. The power rule says that if we have f of x equals x to the nth power, then f prime of x equals n times x to the nth power. We want to show that that is true using the limit definition of the derivative. Now it turns out that the first version of the definition isn't very good here, and we can see why very quickly. We say f prime of x equals the limit as h approaches 0, and then we've got x plus h to the nth power minus x to the nth power divided by h. This isn't good. We don't have a way to expand out x plus h to the nth power because we don't know what n is. So that means we're not going to be able to divide h out of there. We're stuck. But let's back up and look at the other version of the definition. F prime of a equals the limit as x approaches a, and now we're going to have x to the nth power minus a to the nth power divided by x minus a. Now this is good because we actually do have a factoring formula for x to the n subtract a to the n. So let's apply that factoring formula. We will now have the limit as x approaches a of x subtract a times, now we'll have x to the n minus 1 plus a times x to the n minus 2 plus a squared times x to the n minus 3, and we keep on going until we get all the way down to a raised to the power n minus 1. Notice now that we can cancel the factors of x minus a from the numerator and the denominator, and at this point we can replace all the x's in our expression with a's to take the limit. And before we do that, let's actually look at what we've got here. We're starting with x to the n minus 1, and we're going all the way down to x to the 0 power, or starting with a to the 0 power and going all the way up to a to the n minus 1 power. That means that across here we have n terms. So when we take that limit, what we have is a to the n minus 1 plus a to the n minus 1 plus a to the n minus 1, and we do that n times. So that's n times a to the n minus 1. Notice that looks just like our power rule. It doesn't really matter now at this point what this letter is. It's just a variable. So at this point, we can go in there and we can actually replace the a with whatever letter we like. So now we know that f prime of x equals n times x to the n minus 1. We've proven our power rule. So now that you've seen how to prove the power rule using the limit definition of the derivative, take a few minutes and see if you can prove the sum rule using the limit definition. So pause the video, see if you can write out a little proof, and then restart to check your work. Okay, so let's see how you did. We want to prove the sum rule. The sum rule says that the derivative of f of x plus g of x is equal to the derivative of f of x plus the derivative of g of x. So here we go. Let's write down our limit definition for this thing. So we've got the derivative of f of x plus g of x. So that would be the limit as h approaches 0 of f of x plus h plus g of x plus h minus f of x minus g of x all over h. Now, once we've got this, we say, well, wait a minute, let's regroup things. Let's put all of the f's together, and let's put all of the g's together. So now we have the limit as h approaches 0. Now we're going to write all the f's, f of x plus h minus f of x. Now we'll write all the g's, g of x plus h minus g of x all over h. Now, we can go in here and we can split this thing across our addition sign into two separate fractions. So this is the limit as h approaches 0 of f of x plus h minus f of x divided by h plus g of x plus h minus g of x divided by h. But now we have the limit of a sum. We know the limit of a sum is the sum of the limits. So we now have the limit as h approaches 0 of f of x plus h minus f of x divided by h plus the limit as h approaches 0 of g of x plus h minus g of x divided by h. But that first limit is our definition of f prime of x. And that second limit is the definition of g prime of x. So we now see that the derivative of the sum of f and g is the derivative of f plus the derivative of g. And we've proved our sum rule. So if you go back and you take a look in Chapter 3, where we had all those different rules spaced out throughout the chapter, you'll see right underneath or right above most of them, there will be a proof using the limit definition or variation thereof. So take a look back through those and challenge yourself to actually sit down and work through some of those and make sure you understand why those rules are really true. And in your homework, you're going to be practicing using those two definitions of the derivative to take some derivatives. And then once you've actually used the definitions to take the derivatives, you can use your shortcut rules from Chapter 3 to check your work.